operates between 250 Kelvin and 300 Kelvin. Its coefficient of performance is A 6.0, 5 1.2, B 0.8. The COP of Carnot refrigerator is equal to low temperature divided by high temperature minus low temperature, all temperatures in Kelvin square. That is 250 divided by 300 minus 250. The value would be 250 divided by 50. Answer is 5. Taking another problem, a gas contained in a cylinder is compressed. The work required for compression being 5000 kilojoules. During the process, heat interaction of 2000 kilojoules causes the surroundings to be heated. The change in internal energy of the gas during the process is A minus 7000 kilojoules minus 3000 kilojoules plus 3000 kilojoules plus 7000 kilojoules. Now let us solve the problem. A gas is taken in a piston cylinder arrangement. The system is definitely closed because there is no possibility for mass transfer between the system and surroundings. Writing first law of thermodynamics for the closed system, Q minus W is delta U. It is a non-cyclic process. The gas is being compressed, therefore W should be minus 5000 kilojoules according to the sign convention of work transfer. The heat interaction causes the surroundings to be heated, which means the system must have rejected the heat of 2000 kilojoules, which is of negative sign according to the sign convention. Q is equal to minus 2000 kilojoules. Substituting in first law, minus 2000 minus of minus 5000 should be equal to delta U. It should be equal to the plus 3000 kilojoules. Answer is C. Plus sign indicates that internal energy increases. Now let us consider another important problem given in GATE 2007. A thermodynamic cycle with an ideal gas as working fluid is shown below on pressure specific volume thermodynamic plane. One to 2 is a horizontal line, 2 to 3 is a vertical line, 3 to 4 is given as PV to the power of gamma is equal to constant. The pressure at 3 is given as 400 kilopascals. The pressure at 2 is given as 100 kilopascals. The volume at 2 is given as 1 meter cube. The volume at 1 is unknown, given as V1. Now, the above cycle is represented on temperature entropy plane The cycle is put up on the temperature entropy plane as A. TS plane 1, 2, 3. The options were given here. B. One, 2, 3. The arrows were shown in the B option. C. One to 2 is shown as a curve downwards. 2 to 3 is upwards, and 3 to 1 is vertical line downwards. D. One to 2 is a curve leftwards, 2 to 3 is a curve upwards, and 3 to 1 is a horizontal line. Which of them is the answer for the PV plane shown earlier? 1 to 2 process being a horizontal line on PV plane, it should be constant pressure. It should also be a cooling because the volume is decreasing, pressure remains constant. Isobaric cooling means decrease in volume. So in the cooling process, entropy should definitely be decreased, and in a constant pressure process, temperature also should decrease. So which of the curves 1 to 2 in the options will indicate decrease of temperature and as well as decrease of entropy? It is either in C or in D. Looking at the 2 to 3 process, it is the constant volume heating because pressure is increasing. It is a vertical line, it is a constant volume. Because pressure is increasing, it is heating. So entropy must increase, temperature also must increase in the process 2 to 3. So that option is there in C and D. Because constant volume process is steeper than constant pressure process on TS plane. T by CV being greater than T by CP implies the slope of constant volume process should be greater than slope of constant pressure line on TS plane. So C and D both could be the answers, but at the same time, if you look at the 3 to 1 process, which is an isoentropic expansion, that isoentropic process should be shown as the vertical line because the temperature should decrease in the isoentropic expansion. The final answer is C. If the specific heats of the working fluid are constant and the value of specific heat ratio gamma is 1.4 in the above problem, then the thermal efficiency in percentage of cycle is A 21%, 40.9%, 42.6%, 59.7%. The solution could be given as thermal efficiency of any heat engine cycle. It should be heat engine cycle. One minus QR by QS. Q rejected is in the process 1 to 2. That is 1 minus Q1 to 2 divided by heat supply is in the process Q2 to 3. But Q1 to 2 is equal to CV into, since it is a C1 to 2, since it is a constant pressure process, it should be Q1 to 2 is equal to Cp into T1 minus T2. Q2 to 3 should be equal to the heat supplied, because the temperature is increasing at constant volume. The heat supplied in this process is given by Cv into T3 minus T2. There is no heat transfer in 3 to 1 process because since it is reversible adiabatic. Therefore, thermal efficiency of the cycle is 1 minus Cp into T1 minus T2 divided by Cv into T3 minus T2. Cp by Cv being gamma and T2 being taken common, T1 by T2 minus 1 divided by T2 also taken common in the denominator, T3 by T2 minus 1. T2 and T2 are gets cancelled. According to Charles' law, T3 by T2 can be taken as 400 divided by 100, that is 4, because volume being constant, ratio of the absolute temperatures is ratio of the pressures, that is Charles' law. So we know T3 by T2. Coming to the 1 to 2 process, T1 by T2, again applying Charles' law, it should be equal to the V1 by V2, applying Charles' law for the constant pressure. But we do not know what is V1. We know V2 as 1 meter cube, but we do not know V1. V1 could easily be calculated from the process 3 to 1, that is P3 V3 to the power of gamma is equal to P1 V1 to the power of gamma, implies P3 by P1 is equal to V1 by V3 whole power gamma, which is given as 1.4. P1 is P2 as shown in the figure, implies 400 divided by 100 is equal to V1 divided by V3 is V2, which is given as 1 meter cube whole power gamma. Therefore, V1 is equal to 4 to the power of 1 by 1.4. Substituting these values in the above formula, we could obtain thermal efficiency of the cycle. This is the solution.